Hello there. In this video, I'm going to go over the classic proof of the sine addition identity. So that would be sine of, and this diagram uses alpha and beta. So alpha plus beta. Now we're going to take a little cheat and we're going to use the end result of what we know it to be. When this was initially being proved, it probably was not known what it was. So this would be sine alpha times cosine beta plus cosine alpha times, not plus, times sine, one of these days I'll get it, okay, times sine beta, okay? Now this diagram I did not create myself, I just went online and I grabbed an image. I hope I don't get sued. The idea here being that we want to use geometry to prove this identity. So I'm going to go ahead, first of all, I'm going to take a look at sine of alpha plus beta and take a look at what this means considering this diagram, okay? Now notice the very important detail here is that this side right here is equal to 1. That comes in handy because 1 solves a lot of issues when we're doing calculations. And sine alpha plus beta would be this entire angle right here. Okay, so what would that be in terms of the geometric sides? Well, we know sine to be opposite over hypotenuse. That would be this side would be opposite. That would be BF. So I'll write it out. Sine alpha plus beta is equal to BF over the hypotenuse, which is right here. That's equal to 1. So really, it's just equal to BF. Now, we know with the addition sign, addition identity, there's this addition sign right here. Well, having set it up this way, there's no addition sign. We want to work the addition sign into the problem. So I'm going to say BF is equal to these little segments right here. Okay? And so that would be FD plus BD. Okay? Or DB, probably. I apologize if my ordering isn't 100% correct. Please forgive me, okay? All right, so what we effectively need to do is know that, okay, FD is going to somehow be equal to sine alpha times cosine beta, and BD is going to somehow be equal to cosine alpha times sine beta, and this is the whole entire approach to this kind of problem, okay? So sine alpha, let's go ahead and start with that one. I'll do that one in a different color. So sine alpha, so that would just be this angle right here. We're going to use the same approach. Okay, so sine alpha, the opposite side would be CE. So sine alpha, again, opposite over hypotenuse. We got CE over the hypotenuse, which is this side right here, AE. Okay. And now, really quickly, if I were to just multiply both sides by AE, I know I need to be multiplying sine alpha by something that will get me cosine beta. So I'm going to do this, and I'm going to cancel these out so I can end up with sine alpha times AE equals CE. Okay, great. So I've got what it equals. Now, CE has to equal something. But we'll come back to that later. Let's go ahead and focus on cosine beta. Okay, so cosine beta, that would be this angle right here, would be the, not opposite, adjacent side, which would be, hey, look at this, AE over the hypotenuse, which is right here. This is the 1. Well, really, that's just equal to AE. And notice we know what AE equals, cosine beta here. So we end up with sine alpha times cosine beta is equal to CE. Now the idea was to take this, and it should be equal to either FD or BD, because that's what we had in this original part. Well, notice BD right here is part of a rectangle that is opposite CE. So we note BD is equal to CE, which means we have the first part of our solution, okay? So this is equal to BD. Great. We were starting to fill in the gaps a little bit. So let's go ahead and see if we can find cosine alpha. So cosine alpha, it might be initially tempting to say cosine alpha would be the adjacent side here. That'd be AC. So cosine alpha is equal to AC over the hypotenuse, which is AE. Well, if I take the same approach I did with sine alpha and multiply both sides by AE, what I'm going to wind up coming out with is cosine alpha times cosine beta, which is not what I wanted. So that can't be what I need. Well, where else do we see alpha? Alpha is right here. And this is going to be the important one. Why is this side right here alpha? It's because this angle right here and this angle right here, if we extend these lines, are alternate interior angles, okay? This angle right in here would be 90 minus alpha, given the fact that this is a right angle. And so this angle right here would be 90 minus alpha, which quick simplification shows us that's alpha. So that's how we get that. Let me erase those notations so they don't get in my way. But that is the reason why that angle is alpha. Okay, so maybe we can work with that angle to find cosine alpha. So cosine alpha, let's try again. And I show you that just because when I initially went through these myself, that was the mistake I made. And it wasn't until I saw, hey, I need FD. That gets me my adjacent side, FD, over the hypotenuse of this triangle, which is EF. Now I can set something up like I did with sine alpha, multiply both sides by EF, okay? And I get cosine alpha times EF is equal to FD. Well, I still need to work in sine beta somehow. And because of the way things have worked out so far, sine beta needs to include FD. So sine beta, how many times am I going to make that mistake? Sine beta is equal to, well, that's this, again, this angle right here. I apologize, it's hard to see past all my annotations, but the opposite there would be EF over my hypotenuse, which is 1, which is really just EF. And did I say I needed to work it into FD? I really meant I need to work it into EF. That's my mistake. So now that I've done that, EF, I get cosine alpha times sine beta equals FD. And notice here we had this, and here we've got this. So at the end of the day, the sine alpha plus beta is equal to my sine alpha times my cosine beta plus, and then we've got my cosine alpha times my sine beta, and there I've got it. I do plan on doing one of these for sine, the difference identity, and then addition and difference for cosine as well. Thanks for watching.